Hi, this is Abdul Aziz Khan. This is lecture 20 of my basics of microwave propagation. So, like in my previous video, I show you the geometrical representation of reflection, and I show you some very strange type of math. That math was taken from somewhere where it was not very legible as well, because my idea and point was not to take you in very deep details of math, because I don't want anyone to say that, oh, we are not students, we are not the classroom guys, and you are going very deep. So in this video, I will just take you to some approximated, because in math, the good thing is math is that in math can take you in very deep dive, and math can approximate things for you and make it a bit easier for you. So we will not go in very much detail of the previous mathematical formulas that we were seeing, which has some integration, differentiation, and these kind of things. We will go with very simple approximated value, the same formula, but they are not exact, they are approximated, so that they are a bit easier to understand and easier to grasp. But at least we will have some idea that how these things are approximately calculated, so that we can have some more insight of it. So assume that we have something to solve. For example, there is a link which has one antenna or one tower. The height of the tower or height of the antenna from ground is, for example, almost 1496 feet. The second antenna is around 2787 feet. Just don't go exactly in these values, because these are a bit bigger values, so that we at least get some numbers. So the path length is 52 miles. It's a very long path. I've been almost 85 kilometers. The K is 4 by 3. K is not very significant here, but the K value is provided. So you need to calculate the position of reflection point Y with the antenna heights used for these links. Also calculate the multi-part delay and the standing wave generated due to this delay. So calculating the reflection point first, we should calculate the reflection point first, then calculate the lengths of direct and delayed signal path. And we'll take the difference and convert it into nanoseconds. So basically what we will do is that we'll have an incident wave and then we'll have a reflected wave. So we'll calculate the path of the incident wave and the path of the reflected wave, and we will just take the difference of it, and then we will convert that difference with a roughly 1 feet to 1 nanosecond, but we will see that how it is really done. So let's go in a bit of math, because knowing a bit of math is not bad. So what we'll do first, we will convert the main path into feet, because most of the things we have in feet. So as 1 mile is almost 5280 feet, so our link is 52 miles. So we will have 274,560 feet. So the approximate formula for the midpoint or reflection point is that y is equal to d h1 oblique h1 plus h2. This is from the first tower number 1, height 1. Because we have two towers, so the distance from the second tower is that you take the main distance and remove this part, so you will remain with the other. Like, for example, these are two towers, in between somewhere is a reflection point. If you get the distance from one tower to the point, then if you remove this distance from the main distance, you get the other part. So this is a kind of simple thing. So now we will calculate, but because this has the height 1 and height 2 is under the root, so first we calculate both the under roots, like under root 1496 and under root 2787. We get these values and we put these values in this formula. So y is equal to, this is the value of d, and then this is under root h1, under root h1, under root h2. So we get this, that this should be multiplied by 0.429, which gives us a value of 116,100. So we will again make it like here we multiplied it from the 1 mile, I mean number of feet in 1 mile. So here we will divide it, and we get that y is 21.99, almost 22 miles. So if the total link is 52 miles and distance from one tower is 22, so distance from the second tower is simply difference between the total length minus distance from one tower. So this is 30 miles. So if you add both of these, 30 plus 22, you get a total distance 52. So we get the reflection point is 22 miles from one tower and 30 miles from the other tower, because the towers are not at the same distance. If they were on the same distance, this should be same, but the towers are on, one tower is a bit lower, one tower is a bit higher. So now if we want to evaluate the multi-part delay, then the axis path length is approximated by delta L is equal to 2h1h2 divided by d. So it's a multiplication of both the heights and twice of that and divided it by the total length. So you will get the distance between the main and the reflected wave. So we will use the known values that we have. So this comes out to be 30.39 feet. If you remember in the question, the approximation was 1 feet is equal to 1 nanosecond. So 30.39 feet should be almost 30.39 nanosecond. But here we don't go for the approximation. We put the simple formula that basically the delay is the difference between this length and the speed of light. So we take the value in meters, 9.26 meters, and we divide it by the speed of light, which is 3 into the power 8 meter per second. So we get almost 3.09 into 10 to the power minus 8. So we make it 30.9, and this, when we will make this value as 30.9, then this will become 10 to the power minus 9, which is a nanosecond. So the delay comes out to be 30.9 nanoseconds. So now we know that if these are two towers and there's an incident and there's a reflected path, then the delay between these two paths, between main and the reflected path, should be a 30.9 or approximately 31 nanoseconds. So now when we know the delay, and now if we know the frequency and we can get the wavelength of that frequency, then we may estimate that it will be a in phase or out of phase or partial out of phase signal. So my point for giving you some kind of mathematics is that you at least learn something, you at least learn that there is a delay, how it is calculated. When you will be learning any new thing like the signature curves of some microwave, you will know that okay, this is also talking about some kind of delay. So what is that delay? Then you'll know that okay, it's almost same delay. So where this delay is actually implemented. So my point is that you learn something new, you learn some idea, and so that when you are sitting somewhere and when someone is talking, someone is going some in some deep concepts, then at least you have some idea that what kind of things are being talked here. So I hope that this all should be beneficial for you. So let's meet in some of the next video. I hope you will like, you should have learned something new from this video. So if you really like it, then spread it with your friends so that they can also learn. So see you in my next video. Goodbye.